Hello, my name is Jared Hudnall. I'm a fourth-year physics major at the University of California, Riverside, presenting my final capstone project for Advanced Physics Laboratory on the topic of the photoelectric effect. So the photoelectric effect is a very surprising result in physics history that is normally associated with Albert Einstein, but is actually was an experiment that was first conducted by Hertz in 1887 and only correctly interpreted by Einstein for the first time in 1905. So we're going to take maybe a slightly different approach of explaining and understanding the photoelectric effect. In particular, we're going to be looking at it from the perspective of solid state physics and how to look at more deeply what's going on at a microscopic level in the material when you're discussing the photoelectric effect. So what Hertz did in 1887 is he took a device called an evacuated glass chamber that looks a little something like this, and over here it had this quartz lens that allowed a light source that Hertz actually originally used a hydrogen gas discharge tube for his light source, but it has this light source, and it's maybe not so important for our purposes, but the purpose of the quartz here is it shifts the wavelength of the light so that, well, it's not entirely clear yet why the frequency of the light would be important, but we have light entering in through this lens, and it strikes a metal plate that is referred to as the photocathode. I hope I'm writing big enough for that. And here we have the quartz lens. Light enters into the quartz lens, it strikes the photocathode. Again, this is just a metal plate, and there is a similar metal plate on the other side of the evacuated glass chamber. This we'll call the anode. And both the anode and the photocathode are attached to leads, that is just metal conducting wires that leave the gas chamber and are connected to either side of a battery. So hence the cathode and anode portion of the diagram here. So there are 3 degrees of freedom in the photoelectric effect experiment that we're interested in. The first is the intensity of the light that's being shined into the container onto the evacuated glass chamber and onto the photocathode plate. There is the frequency of that light is another degree of freedom. So what's the color of it? And the voltage between these 2 plates, that is the voltage of the battery that we're connecting them to, is another degree of freedom that we have in this experiment to try to investigate some of the physics that's going on. So the first case that we will consider, and the simplest, is the case of a 0 voltage bias. And in order to investigate what happens when we have a 0 bias voltage, is we have to discuss more microscopically what is going on here in the photocathode plate. And in order to do that, I'm going to make a diagram of so this is a conducting plate, and conductors are characterized by free electrons. They have an extraordinary amount of electrons that are freely floating in this material, able to conduct electricity and able to move freely throughout the lattice and through the wires and travel. Obviously, if there's no bias voltage, there's no reason for them to. But let's just come up with a diagram to kind of describe the energy of all the electrons in the photocathode, kind of nominally, at the basic, without doing anything. In order to do that, I'm going to create a y-axis here that will represent the energy of an electron. So for instance, if I put an electron here, then it has an energy at this level. An electron over here is at a different position in the lattice. So on my x-axis is almost going to be it's almost going to tell me where I'm at on the plate. So this electron is at a different position, but it has a higher energy. And this one maybe is at roughly the same position, but has a lower energy. Okay. So what I'd like to do is describe this plate. So first, an energy scale that we are interested in for the purposes of the plate is, say, here. And we'll tell you what the significance of that is. So for our purposes, this mark that I just put here, I'm denoting with a W. And this energy is going to represent the energy of the well. That is to say, the energy of the lattice and the energy that an electron would need to escape the lattice. So if you have an electron with an energy anywhere above this dotted line, then we say that electron has sufficient energy to escape the lattice. And what it'll actually do, if it escapes the lattice, is it will, with whatever energy it has left over in the form of kinetic energy, escape this lattice and travel through the tube and strike the anode. You can imagine once we plug in the battery, it's going to be, once it has enough energy to escape this lattice, it'll be attracted towards the anode. So that's the first energy we want to talk about. The second is neglecting any kind of thermal effects. So working, like a zero temperature. We have another energy here that I'm going to designate with a little EF. This is referred to as the Fermi energy, and what this energy represents is this is the highest energy of the electrons that are sitting in the metal. So obviously this is lower than the energy of the lattice, we would expect that. So there's just a bunch of electrons down here. There's just a whole bunch of electrons. This area of the energy diagram that I have here, in this lattice, is referred to as the Fermi sea of electrons. So all of these electrons are living here. None of them have sufficient energy to escape the lattice, or else they would have already done so. And all of them are stuck on the plate and just kind of sitting here. Nothing particularly interesting happening at the moment. Now, we do something rather interesting, which is, so actually one more piece of jargon to get out of the way is the difference between this Fermi energy here, where the electrons are sitting at, and the energy of the lattice, the binding energy of this cathode plate, is referred to as the work function. So the work function represents the energy that you need to give an electron in order for it to successfully escape the lattice. So if you give it just enough plus a little bit energy equal to the work function, then an electron at the top of this Fermi sea will be able to escape the lattice and travel through this vacuum tube. Okay, so with that out of the way, we are looking at just a zero bias voltage. And with a zero bias voltage, the only thing that could possibly give any of the electrons any energy is the energy of the light that's being shined on them. So let's go ahead and represent that on our diagram. So what will happen is this light is shining on the plate, and this light, we know electrons can absorb some of the energy from this light and use that energy to try to escape the lattice. So here we have the energy of the light. So say, we shine the light, individual electrons consume the energy of that light, and they escape from, say, this energy to this energy. And now you can see they have this distance. They have this amount of energy left over. This I'm going to represent with a T. The T is going to be the kinetic energy of the electron. So it's escaped the lattice now. It's traveling through the evacuated glass chamber with an energy of whatever it has left over. So it used this to escape the lattice, and all of the rest kind of goes into the speed of the electron as it's traveling through the evacuated glass chamber. So there are some very simple mathematical results to come from this. The first is that the work function, this guy, the binding energy of this lattice, is equal to the total energy of the light minus what it has left over. And if we rearrange to solve for the kinetic energy of the electrons, then we obviously have the energy of the light minus phi, the work function of the lattice. Okay, so we're going to use that result later. So let's discuss now case 2. So case 1 was the bias of the battery was 0. So in other words, we just connected the plates. There's no voltage across the terminals of the battery. Now we're going to add a voltage. And we're going to say that the bias voltage in case 2 is going to be positive, or greater than 0. So we apply, and by greater than 0 in this case, what I mean is that the charge on the anode is going to be positive with respect to the voltage on the photocathode, which will be negative. Now, as soon as you plug in this battery, it's essentially just going to act as a capacitor, and the charges on the plates are going to move until the voltage between these two plates is the same as the voltage of the battery. This is, commonly understood kind of basic circuit analysis. And now the situation is slightly different. So because there's a positive voltage on the anode, electrons want to travel to hit that plate. It becomes easier for them to make that journey because we've introduced we've made it more energetically favorable for them to do so. So with that in mind, the work function of the lattice, the energy that you need to give an electron in order for it to escape, actually goes down. So say the energy that we gave it, that representing the energy between these two plates, is, say, here. This is the charge of an electron times the bias voltage of the battery. And now the energy required for an electron to escape the lattice is effectively lower now. So it only requires a small amount of energy for an electron to escape the lattice and gain some kinetic energy and travel across the evacuated glass chamber to the anode. So the new expression in case 2 to describe this situation kind of mathematically is that the effective work function, which I'm actually going to give a little prime to as well, is equal to the total energy of the lattice, which we've called W, and it's going to be minus the Fermi energy and minus the charge of the electron times the bias voltage. Again, this is a result that will kind of come into play a little later. So the final case that we're interested in is for the only one that's remaining, which is, let me erase some of this, a negative bias voltage. So V bias now less than 0, negative. In other words, the anode is now negatively charged with respect to the photocathode. In other words, electrons are going to be slightly repelled by the anode. And so you're going to have to give it actually additional energy. You're going to have to give the electron energy to not only overcome the binding energy of the lattice now, the plate, but also it's going to have to overcome this, basically the energy of the battery. It's got to overcome this charge that you've put on the anode. So that is essentially the situation in reverse. So you have E, V bias, and now your effective work function is higher. It's the exact same situation, but in reverse. So now the effective, how much energy you have to feed an electron in order for it to successfully escape the lattice and travel to the anode with some kinetic energy T is now higher than it was in either case 1 or case 2. And there's something very interesting actually. You can tweak the bias of this battery in order to fully match the energy of the light, because what you see what will happen is if I raise the bias voltage so that T gets smaller and smaller and smaller, the kinetic energy, the leftover energy that the electron has gets smaller and smaller and smaller, then effectively what I've done is I've stopped all of the current that flows that I've been measuring, right? So the thing that I've been measuring in this experiment the whole time is current. How many electrons are escaping from the photocathode to the anode. And if I raise this bias voltage sufficiently such that it totally shuts off the current, then I have an experimental determination of the effective work function of the lattice, and therefore the energy of the light. And that's kind of what we're interested in from the get-go. So the start of quantum mechanics comes with this idea of what actually gives light energy. And the results of the photoelectric effect tell us about that. So, okay, nothing that I've described so far has contradicted classical theory at all. This is all very well known. Every part of this was pretty well understood, and there's nothing surprising here. So all we have to ask ourselves is, you're in 1887, you're Hertz, you're conducting this experiment. What does classical theory predict? What does Newton's mechanics predict? It's worked for 200, 300 years at this point. And what is the prediction of that model? Well, the first prediction is that if I increase the intensity of the light, then I will excite more electrons and the current will increase. That's one prediction. Another prediction is that light of any frequency, if you make it intense enough, it will generate current. So in other words, the color of the light, according to classical theory, is not important. It's not a factor, and as long as you make this, you can do one of two things. You can either increase the intensity of the light or just let it run for longer. And that energy that the light is delivering to the plate will increase over time, and eventually it'll have, the electrons will have enough energy to escape the lattice and you'll get current. As long as you wait long enough or you increase the energy of the intensity of the light. Now let's say we actually conduct this experiment at this point. What do we observe? Well, the first surprising result is for a given bias voltage, for a given voltage of the battery, light of a certain color below some set frequency will never generate current no matter what. You can crank up the intensity as much as you want. You can let this experiment run for as long as you would like to. There are certain colors that will, below a certain frequency, that light will not generate any current whatsoever. This is a very surprising result. Another result is kind of the complement of that, which is that for a given bias voltage, light above a certain frequency will generate current, and the amount of current it generates is proportional to the intensity of the light. So above this frequency, things act exactly as you would expect, and you make the light more intense, and it does drive additional current. That's another result. And another observation is kind of what we already alluded to, which is that tweaking this bias voltage will allow you to stop any flow of electrons. That's not surprising. What is surprising, however, is that this stopping voltage is found to be completely independent of the intensity of the light. In other words, for a specific color, there is a bias voltage for that color that will stop all of the current. Even if you get the most intense light beam possible, it doesn't matter. And a small, whatever, the same battery will stop all of the current for light of that specific color. Okay, so those were all results that Hertz knew about. Hertz knew every single one of those results, and people did for 20, 30 years up to Albert Einstein. And Einstein, working at like a post office at this time and not a leading physicist in the field, is the first to have correctly interpreted those results. So what were his interpretations? The first interpretation is he kind of built on the work of Planck. So Planck, in a completely different experiment, used this result that the energy of light, in again, a completely different experiment, no reason to necessarily suggest that this would be applicable to this experiment, but Planck found that the energy of light was exactly proportional to the frequency of that light. I'm using nu here to represent frequency. The energy of the light is exactly proportional to just the frequency. It doesn't depend on the amplitude of the light, in other words, the intensity. It depends only on the frequency with the introduction of some constant, which he called h. So there's some proportionality constant to make the units work, but the energy of light is proportional only to the frequency. So, Einstein kind of introduced this result that the energy of light is proportional to the frequency. And by graphing this bias voltage, Einstein was actually able to do a kind of a y equals mx plus b determination for Planck's constant, which is very interesting. So he made a very predictable result. Now, this is all well and good. It does not resolve the result that increasing the intensity when you're above that stopping frequency. Once you're above that frequency and you increase the intensity, it does drive more current. But you're not, according to this, you're not delivering any more energy into the system. The energy of the light is the same. So why would increasing the intensity of the light under that circumstances result in more current? And Einstein's answer was that light only gets exchanged in quantized amounts. So there are little indivisible packets or quanta of light that get exchanged with electrons on a one at a time. And this quantized nature of light was very controversial, but explained why the intensity of the light would drive more current. Because if you have, so what he called these, the English translation is photons, and if you have photons of a frequency that gives them insufficient energy to excite the electrons into escaping the plate, then it doesn't matter how many photons you fire at the plate, it'll never drive any current. But if they do have sufficient energy to excite electrons, and you fire more of them, then they'll excite more electrons, is the kind of interpretation that Einstein threw on. So higher intensity leads to more photons, and more photons are able to interact with more electrons, and more electrons means more current. And so Einstein's interpretations of the results of the photoelectric effect, kind of taking this kind of solid state physics approach, allowed him to explain all of the surprising results that were not corroborated by classical theory. Now, this was an extremely contentious result, and very famously, Andrew Millikan a famous physicist who would later on go on to win the Nobel Prize for his work with the photoelectric effect, didn't think Einstein was correct at all, and actually spent the next 13 years or so doing very, very, very high precision measurements of this proportionality constant in order to prove that Einstein was wrong, and instead ended up winning a Nobel Prize for coming up with the most precise measurements of Planck's constant that had been known up to that point, and with a great deal of accuracy and precision, proving Einstein correct. So that's the photoelectric effect from kind of the perspective of solid state physics. Thank you very much for watching.